As impressive as man's technological achievements are, they pale by comparison with the powers at work in creation. In a single day, the Earth's atmosphere generates more power than the energy man's technology is capable of producing in an entire year. What is the source of this limitless natural energy? Who has created the continually thundering Earth, with its whirling winds and the roaring waters that cover most of its surface? These are the questions that have been at the heart of our efforts to understand ourselves and the world we inhabit. A world energized by forces so awesome they can only be understood as God's handiwork. Hello, I'm Jim Pemble, your guide for this exciting series that explores the great forces within the natural world. We're going to set off on a journey of discovery that takes us down some of the mightiest rivers of the world and see what happens when they reach over their banks to form great floodplains. We'll witness the effects of flash floods. We'll examine one of the most unusual results of undersea earthquakes, those massive oceanic waves called tsunamis. We'll learn about the engine that drives many of these occurrences, the Earth's atmospheric weather. And we'll explore the attempts made by modern science to predict and control some of these events. Join me now as we circle the globe, buoyed along by the planet's greatest resource. Prepare yourself. You're about to be swept away by the roaring waters of the world. Floods are by far the most often occurring rampages in nature. Yet they are also nature's most difficult aberrations to quantify, because there are so many differing circumstances which contribute to them, depending upon their location.
I was in high school when 1964 flood hit Northern California. And there was just this incredible amount of water that just came out of the mountains and down the rivers, and the rivers went up over the banks, and everything was water. And some of I had friends who literally, the houses came up off the foundations, and their houses went down the river, and they climbed up through, poked a hole in the roof and got up on the roof and were rescued off their house as they floated down the river. And their cows were killed, and it raised havoc with the entire community.
Rain was coming up, the water was coming up. They were just like moving upstairs, trying to move everything upstairs. It was coming up the stairs. And when the power went off, everybody in the apartments kind of got together and was making a round to make sure everything was all right. I had a cousin, Dan, was trying to come down the street, and we were telling him not to drive in the water. He had a pretty nice car, a Lincoln Town car, and you could just see his wheels going under a little at a time, and by the time he got to where he realized it was too deep, it just swished him across the street.
Floodplains, those places where rivers reach out and claim nearby lands on an average of every 100 years, are the most likely places for seasonal flooding.
The 100-year floodplain is just simply the area that's expected to be underwater on the average once every 100 years. It does not mean that once a century. It may happen 2 or 3 times a century, and then you'll have 1 or 2 centuries where you don't see that sort of phenomena. So there's no reason to be reassured that if you've seen a 100-year flood, you're out of the woods for the next 100 years.
Many of the planet's floodplains were created by the slow, inexorable movements of glaciers. This time-lapse sequence offers some idea of how glaciers, little by little, gouge their way through enormous expanses of the Earth, carving out what later become river valleys. According to some scientists, the scenery of today's few remaining glaciers may be harbingers of the future. The varied climate of today's Earth, with ice reduced to the polar caps, could be but a short interlude between the last deep freeze and the next one. Along the seacoast, floods can be caused by great sea surges during storms, propelled by the engine of the Earth's whirling winds, especially at times of high tides.
While hurricanes are the phenomena that are most typically associated with storm surge because they are fairly dramatic, the onset is fairly rapid, There are other major storms specifically affecting the Northeast that do very large amounts of damage. These are called northeasters. They will sit over the coast or off the coast of the Atlantic, pushing water much like a hurricane. Although the winds aren't quite as intense, they may be 40 or 50 miles an hour, they may last for days, and oftentimes there's tremendous coastal erosion associated with these northeasters.
The tides, the seasons, the day-to-day variations in weather, each makes a contribution to the world's roaring waters.
The first time I was ever on a sailboat, a big sailboat, was a 28-footer. It was about 1981, and it was off of Key Largo. I looked up a grade school buddy of mine who lived in Miami, and he had just bought a 28-foot sailboat. We went sailing off of Key Largo. We were out there, it was gorgeous, wonderful, and a squall came out of nowhere. A squall is a big rainstorm, and all of a sudden we had 15 to 20-foot seas. This 28-foot sailboat is literally surfing down the face of these swells. It was very thrilling, but I did think I was going to die at sea.
There are many influences that exert themselves on the world's bodies of water. The greatest influence is the sun. Our nearest star is always at work, drawing water into the sky, where clouds form that eventually drop their accumulated masses of water back to Earth. This cycle is ongoing, and without it, there wouldn't be any weather at all, much less roaring waters. The ancients were aware of cyclical patterns in the weather. Nearly 3,000 years ago, Solomon wrote that all streams flow into the sea, yet the sea is never full. To the place the streams come from, they return again. Solomon may have understood the function of the sun in drawing water into the atmosphere, far more than we realized.
Certainly in the atmospheric sciences, in hydrology, we see power that is unprecedented. It is subtle, and oftentimes people miss it. There are 1,000 lightning strikes a minute across the globe. Each lightning strike could probably keep a small city electrified for an hour. When you look at that, the atmosphere and the environment is just simply processing such tremendous amounts of energy. It makes things like the nuclear bombs that we drop and have puny.
Moisture goes on a continuous cycle. At the surface you have lots of different ways of getting moisture into the air. You have evaporation off of the ocean, where you have small particles of water that automatically jump into the air almost from the top of a water surface. You have it evaporating off of snow surfaces in the mountains. And so moisture is getting into the air that way. Very small particles of water floating in the air continuously. And then as the condensation in the air, the droplets that are condensing become bigger and bigger and bigger. They eventually fall out of the cloud, and then you have your precipitation. So first of all, the water vapor goes into the air. Then as it cools in some method, it condenses, and if you have enough of the water, it will precipitate out.
It's the great masses of cold, dry air and warm, moist air that really stir the cauldrons of the Earth's weather. Many skirmishes take place continually around the globe. Battles between competing air masses, which meet along borders that, as on the battlefield, are called fronts. There is one main line of battle drawn along the polar front, which separates the cold, dry air masses of the polar regions from the warm, moist air masses of the tropics. About 100 miles wide, this front circles the entire Earth, with warm and cold air making warring advances into each other's territories all along its borders. If one army of cold air or one of warm air advances deep enough into the territory of the other, a low pressure zone may be created, drawing air higher into the atmosphere. As the battle rages, The front buckles inward on one side of the lobe as an intrusion of warm air swells up and over the denser cold air mass, while cold air twists tortuously under the mass of warmer air. The sluggish warm front is no match for its colder, swifter adversary, and the weather disturbance eventually works its way to its highest intensity. Finally, the victorious cold front tires of the battle, and all grows quiet until another incursion starts the cycle again. But this scenario describes only one isolated skirmish, a single battle taking place upon a gigantic battlefield. At the top of this atmospheric warfare, great bands of wind, the jet streams, howl their way around the globe, spreading the atmospheric chaos around the world.
And it looks like a big snake. And where it's heading north is where it's trying to transport warm air to the north, move that warm air north and balance that temperature differential. Where it's heading south, you'll see it's trying to push colder air to the south, again trying to balance that temperature differential. Inside that jet stream curve that circles the globe, you'll find smaller storms that do the same thing, actually circulate air, bringing cold air down the backside, pushing it south, warm air up the front side, pushing it north. And this whole thing is a big balancing act.
There are 2 or 3 jet streams per hemisphere, and each can blow at speeds up to and over 200 miles per hour. One of the most influential jet streams is in the so-called mid-latitudes of the atmosphere.
It's enhanced by a temperature boundary, and the area where you'll find the largest temperature differential is in the mid-latitudes. It's that area that bounds the warm tropical areas from the cold polar areas. And it's an area where over a short distance you'll find a very strong temperature gradient. That is where you'll find the jet stream, directly above that area on the surface where you find the very cold temperatures. And the jet stream is located up in the upper troposphere, anywhere from 25 to 35 or 40,000 feet.
Just as an internal combustion engine uses countless continuous explosions of oxidized fuel to keep running, the atmosphere is provided with the energy it needs to stay in motion from its own explosions. Storms within the prevailing winds. Storms that supply immense amounts of heat energy, conveying it back into the atmosphere as momentum. The whirling winds of a planetary weather machine that at any given moment is seething with 2,000 storms around the globe, about 16 million a year. Little wonder that this continual atmospheric activity supplies the world with abundant amounts of roaring waters.
Some areas have more moisture content, some less. Desert areas tend to be a little drier. And then the coastal areas where you have a lot of ocean surface, water surface, you have a lot of moisture, a lot more moisture. And also areas where you have a lot of greenery, southeast part of the United States. Also flow off the Gulf Coast, you have a lot of water.
Regardless of where people have chosen to live, from coastal regions to far inland river plains, from New England to the far-flung islands of Japan, storms and their consequences have been a regular part of our history on this planet.
When you realize that you are totally out of control and that this river that came up over its banks was in absolute control of everything in its way, and that we just kind of got out of harm's way and waited for it to go down, it changes everything. You realize that you're not in control and that you are just going to do what you have to do to survive this thing.
The wind speeds generated by the jet streams and the countless storms created by clashes of warm, moist air with cold, dry air make it apparent how weather changes can come upon us as quickly as they do. And it's these rapid changes that are responsible for an occurrence which appears with the lightning speed its name suggests, the flash flood. When a thunderstorm comes through an area, it can dump a rather amazing amount of moisture in a fairly short period of time. The average thunderstorm drops 125 million gallons of water. Where's it all to go once the ground is saturated? In addition to the water that accumulates once the ground is soaked, All that water can cause dams or levees to give way.
We were getting a tropical storm, and a bridge that I had to go over in order to get home was actually out due to the storm. And there were cars that were all on the side of the road because they had been blown over or washed out. And that actually lasted about 3 or 4 days, where people didn't even go to work because the roads were washed out, and a lot of damage was done to houses and a lot of flooding.
Our street was like a valley, and it started rising on our street maybe about a couple of inches, and I went and got my camcorder and just was filming it. Had a cousin stayed like cat-a-corn across, and we were just measuring the water, and I mean, like in 20 minutes it was all the way up where you couldn't even see the grass, the curbs, or anything.
The water falls much faster than it can run off. In flat areas, this water tends to pond, providing problems for motorists. Oftentimes they'll drive into them, get themselves in trouble.
There's nothing you can do. Nothing. That water don't look like it's that strong, but man, it's strong. We was out there, when we was swimming out there in it, we'd stand up in some spots and it would just take you off your feet. You might end up about half a block down the street.
But by far the most dramatic and most severe sort of flash flooding occurs in mountainous areas, small valleys. We get a small core of rain falling over the up portion of a valley. It just has no place to go. It gets funneled into a very small area and then comes rushing down the valley in this tremendous wave. It's devastating. It will wipe everything out in front of it.
The downpour, especially in low-lying areas, rapidly fills an arroyo or valley with tons of rushing, roaring water that can form rapids like some great temporary river. The temporary but overpowering hydraulic forces generated by the roaring waters of a flash flood often move great boulders and tear up trees, completely changing the landscape in minutes. As little as 6 inches of water can sweep along most everything in its path. Even the winter months aren't immune from this onslaught of nature. Ice jams sometimes give way in a river, causing a sudden surge of pent-up frigid water. But what of the floodplains? The products of regular seasonal flooding produced by the world's great rivers that periodically overflow their banks. What causes these usually gentle giants to create some of the most intense moments in nature's high drama?
What's happened in modern times is man, simply because that has always been man has always been fascinated with water as a transportation medium, as a way to explore in the 15 and 1600s. We've always wanted to be near water, settle near water, oceans and rivers. What we've done now is we've tended to, in particular in the United States, concentrated the majority of our population in areas near water because that's where man wants to be. The downside to that is we have put structures and people in places that we can expect to flood. Not every day, not every week, not every month, not every year, but every century. So we have now created a culture where we have put people where we know we're going to have flooding.
There is virtually no landmass on Earth that doesn't experience its share of flooding, although some locations are much more prone than others. Those places in the American Midwest, South America, Africa, and Asia, where enormous river systems flow, for example. Here, people are often regularly reminded that despite all our technology, we still cannot control the flow of water. We need the occasional reminder. In ancient times, people were humbler than we. They knew that God alone ruled over the surging sea. He alone could open up the streams and dry up rivers.
This sort of flooding is a result of very widespread, long-duration rainfall. All of the tributary rivers collect rainfall and start feeding it into the main stem river. Large rivers rise up and inundate the floodplain, much like what happened in 1993 along the Mississippi Basin. And as a result, it's much like a funnel. All of these things are collecting it over a period of time. The river rises, and there's tremendous power here. In the last century, we have recognized the disruptions flooding can cause to our society because we live along bodies of water. And we have attempted to manage those floods to the benefit of society. We have been very effective at doing that for routine floods. The most extreme floods are so powerful that man is just simply puny in front of them. And so most of the construction projects that we have had to address the flooding issue have been very, very effective at what they were supposed to do. They were supposed to address the flood that occurs once every 5 or 10 years, to keep the farmer in his fields every year through the period of 5 or 10 years. But again, when we get something like we saw in 1993, there is no engineering structure that we're going to develop that is going to be able to withstand this power.
In India and Bangladesh, it is an annual occurrence for moisture-laden air from the Bay of Bengal to drench the Himalayas, bringing heavy rains that often flood much of the country. Seaborne typhoons are another source of Asian floods, where heavy rains and tidal waves sometimes accompany monsoon flooding. After an average season's rainfall in Bangladesh, about 20% of the country is underwater. That's every year. When heavy rains fall, the entire country is submerged. But it's not necessary to live in Asia to feel the effects of flooding near the mouth of a river. Sometimes it's not necessary to live near a river at all.
Coastal flooding is primarily the result of large storms. We most typically associate it with hurricanes. Hurricanes come in, the wind is moving in one direction for a long period of time, and it literally pushes a wall of water ahead of it. And as the water approaches the coast, it just rises up and produces what's called a storm surge. Typically the storm surge with major hurricanes is as much as 5 to 25 feet above the normal tide. When storm surges come in conjunction with high tides, they can be devastating, especially for island areas such as the Florida Keys or the barrier islands on the East Coast.
And on it goes, season after season around the globe. And although there is a certain amount of predictability due to anticipated melting snowpacks in the mountains where rivers originate, as well as expected seasonal storms, there are some factors that lead to very unpredictable variations on these themes. Every few years, the waters of the Pacific Ocean along the coast of Ecuador and Peru develop a warm current called El Niño, Spanish for the child, an allusion to the Christ child, since El Niño first appears right around Christmas time. When it comes, El Niño brings with it anything but childlike consequences. From mudslides and flash floods in California to drought in Africa, El Niño earns its reputation for being a capricious climatic event that brings or steals the Earth's roaring waters at will. Usually the trade winds push the warm surface waters of the Pacific toward the west. Cold water rises to the surface, creating fertile conditions ideal for the tiny plants and animals which undergird one of the world's richest fisheries off the coast of South America. El Niño reverses this cycle, and the results are dramatic.
Tend to have much, much warmer water temperatures because you do not have this upwelling along the west coast. So you lose the nutrients, you lose the fish, you lose the birds along that area, and one of the big impacts of an El Niño is the loss of the mining of bird guano along the oceans on the coast of South America, because the birds are gone, because the fish are gone, because the plankton are gone, because the upwelling's not there.
When El Niño arrives, it leaves a convoluted trail of topsy-turvy weather and other effects felt all around the world. From floods caused by excessive rain to droughts created by long periods without rain.
We would see a big cloud of dust coming. Well, it'd be cloudy, and the dust would start blowing, and there was no way, there is no houses that is tight enough that it doesn't get in some, and sometimes it would last all day and all night. It came day after day. It'd skip days, and then it'd be another few days of it. And I don't believe there's ever been a time before that or since then when there were so many dust storms, and you just dreaded the next day or two that came. You just about get the dust cleaned out where you could stand it, and then it would be back.
And then there's La Niña, another offspring of the elements that also causes erratic ebbs and flows of the world's roaring waters. La Niña reverses the trend of El Niño.
We tend to see cooler temperatures than normal and heavier snowfall in the Pacific Northwest than we would with an El Nino condition. And often we don't see the results of that temperature differential for several months. They're measured with a thing called the Southern Oscillation Index, or SOI, which is a pressure differential between Tahiti and Darwin in the tropics. Typically look at the, I think, 3-month time frame of Southern Oscillation Index from like July, August, September time frame to see what's going to happen in the wintertime.
In 1988, La Nina brought drought to the American Midwest and floods to Bengal due to the strong high-pressure system that it created and held in the Pacific. Whatever causes El Nino and its counterpart La Nina, they are known to be part of the primary driving forces behind the roaring waters of the world's climate cycles. Yet as massive as all this weather can seem, including today's floodwaters, nothing compares with the floods of the past that have left their permanent scars on the Earth. All across the globe, there's evidence of what scientists refer to as the super floods of the past.
The flood of record is one that Noah dealt with. Not the agency, but the biblical Noah. Floods have been around for eons. They're part of a natural phenomenon, the cycle that we see.
Superfloods are usually the result of melting, receding glaciers that created colossal deluges that became walled into enormous lakes surrounded by ice dams. Eventually, the walls of ice would crack under the pressure of millions of cubic feet of water, and an unimaginable amount of icy water would be suddenly released. The great floods of the world, past and present, provide us with one of the more impressive and regular examples of the ways in which humanity is subject to the forces of creation. But every so often, the usual is overshadowed by the extraordinary, and the world's roaring waters come crashing down in walls of liquid fury that can numb even the most vivid of imaginations. In English, we call them tidal waves, although they have nothing to do with the tides. Their Japanese name tsunami, meaning harbor wave, is much more indicative of what they do when they arrive on land. Tsunamis are gigantic waves of water that curiously are practically invisible as they race across the open water at speeds of 500 miles per hour. At such speeds, these great waves can move across the entire Pacific Ocean in less than a day, losing almost none of their power as they make their way across vast expanses of open ocean. Although volcanic blasts can give rise to them, tsunamis usually are created by the disturbances of earthquakes on the floor of the sea.
A tsunami occurs when the surface at the bottom of the ocean is changed over a large area. So this generally happens in an earthquake. When a large earthquake uplifts or drops a large section of the seafloor, even if it's only a few feet, it represents a tremendous volume of water. And when that water goes down or goes up, it has to return to its level. And that creates a gigantic wave. Much the same way as if you, in your swimming pool, pulled up the plastic liner and watch all the water rush to one end. This is similar to what happens in a tsunami. And scientists call tsunamis a shallow water wave. Now, you might think that's odd, it's happening in the deep ocean. But when we say that, what we mean is that the ocean looks shallow to the wave. That's how big the wave is. And so the wave is, when the wave is this large, it travels very, very fast. It's traveling several hundred miles an hour in the deep ocean. But it's not very big out there. In fact, you can barely notice it. But when it comes into shore and the depth of the water gets shallower, then all that energy piles up and you get a gigantic wall of water that will rush across the shore. And unlike a regular wave from a storm, this one doesn't go right back in a couple of seconds. This one keeps coming for several minutes, and so it can drive well into land at a very high velocity.
In Whirling Winds, another program in this series about the awesome forces of God's creation, we've explored many of the technologies being developed and used today to predict and track the kinds of weather events that can lead to problems. Stationary and orbiting satellites provide real-time images of storms as they move across the planet. New Doppler radar installations allow meteorologists to track the movement of storms as well as their compositions. Complex mathematical computer modeling lets scientists explore the dynamics of winds and other storm-related factors. Seismic devices are in place at hundreds of locations around the world to monitor volcanoes and earthquakes, which, as we learned a moment ago, can lead to the roaring waters of a tsunami.
What we're looking at here are the 4 most recent events that we've formed in our automatic system here. 3 of these events occurred in Chile. We had a very large earthquake in Chile on July 30th, and today, 4 days later, we are still getting several large aftershocks from that major event. The technologies used to gather this data include the sensors themselves, mostly seismometers, but we have some high-tech seismometers we call arrays, which are many seismometers put down in a special geometric pattern on the Earth to improve our ability to record the vibrations. In addition to the seismometers, we use a variety of communications facilities to get the data back here, including satellites, networks, even undersea cables. We're also beginning to incorporate data from what are called hydrophones. They're special instruments that are like seismometers, only they're deployed in the water.
Just like we use light in the air to look at the world, we use acoustics underwater, sound, and the Navy, U.S. Navy's been using sound for many years, listening for underwater submarines, and they've constructed a large underwater listening network, which is called SOSUS, which stands for Sound Surveillance System. And in 1990, with the wind down of the Cold War, our NOAA program was given the opportunity to tap into some of the underwater cables that are listening to the ocean. And so beginning in August of 1991, we began recording data from the Navy listening station that's based on Whidbey Island, Washington, and Puget Sound, and began recording signals, and immediately discovered a whole variety of undersea phenomenon that's including earthquakes, large marine mammals, a lot of man-made noise, propeller noises, explosions from geophysical ships, etc. Our main interest at the time being undersea earthquakes and undersea volcanic eruptions. The success that we've had with the Navy SOSUS system has led us to want to look at other areas of the world ocean. In particular, there's an area in the central East Pacific Rise, which is the fastest spreading center on the planet and should be the most active volcanic system. However, that area is not covered by the Navy SOSUS, which is restricted to areas of military interest. And we developed here within our laboratory an underwater hydrophone system, not as elaborate as the Navy's system. It's a single hydrophone. It's designed to be deployed in the ocean, tethered on a cable up to the sound channel level. But it's designed to sit for 6 months to a year and record acoustic data continuously. And this instrument right here is the guts of it. And what you're looking at is a full computer here, and a series of 2.5-inch hard disk drives that can hold over 4 billion bytes of data. That is a sufficient rate to allow us to record 100 samples a second over the course of a year. It also has a very accurate clock and a series of filters and amplifiers. And if you think about the difficulty of having a laptop computer run for more than 5 or 6 hours, you can see the part of the technology involved here is getting this instrument to consume little enough power that it can actually stay in the ocean and work for up to a year. We take the information, the wiggly line, so to speak. We do sometimes actually listen to it, but we have to speed it up because human hearing, most of the phenomena we're interested in are below human hearing, but we can speed it up to listen to it. But what we do more often is actually decompose the signals into a graph of time versus frequency. And some of these parallel lines in here, those actually represent the sound of the propellers of shipping, probably merchant shipping. And I picked this piece because this rather large event you see right here is in fact an underwater earthquake. I don't see any whale calls on here, but we were a little early in the year for that. But often we'll see blue whales, fin whales, perhaps sperm whales. And during the most recent expedition, we encountered a group of sei whales, and were able to get out in the field and in a small boat and take a recording on site. So we'll know what they sound like, and using this, we may be able to look at the migratory patterns of large whales in addition to studying earthquakes.
Some research is being done just for the sake of the knowledge it can bring us about creation. Off the Pacific coast of Oregon and Washington, for example, scientists are monitoring vents, geothermal openings on the ocean floor where two tectonic plates meet.
The Vents group is interested in seafloor processes that are occurring at the Juan de Fuca Ridge, which is an area of active seafloor spreading that lies about 300 miles off the coast of Oregon and Washington. And the Juan de Fuca Ridge is an area where the seafloor is actually splitting apart, and it's causing two plates to separate from each other. And one of the neatest things that's happening right now is that there are these areas called hydrothermal vents. They're like hot springs on the seafloor. And our group is interested in mapping the locations of these vents and also mapping the other geological and chemical processes that are associated with them. We're doing what's called pure basic science. And basic science is concerned with finding out how the Earth works just for curiosity's sake, and just so that we know as much about the Earth as possible. Now, in the long run, perhaps an oil or gas exploration outfit might want to look at our work, because the hydrothermal vents do have some valuable minerals in them, such as sulfur, zinc, copper, even a little bit of gold. And it might be possible in the long run to actually mine the seafloor for these minerals. But right now we don't really know enough about what's going on with these vents, because they've only been mapped. I think only 1% of the hydrothermal vents on the entire global mid-ocean ridge seafloor spreading system has been mapped at a sufficient detail that we know what's going on.
We might be tempted by fear and misunderstanding to see the thundering Earth, its whirling winds, and its roaring waters as threats to our very existence. Yet where would we be had not God, in His infinite kindness and wisdom, set these great natural forces into motion during the creation?
Well, using the analogy of a river system being something similar to the vascular system in the body. The vascular system in the body is there to move nutrients throughout the entire body. And rivers in that sense are somewhat similar. Rivers are simply a way for nature to take rainfall, which occurs every place, and move it back to the oceans to complete the hydrologic cycle. Flooding is simply nature's way of rearranging its furniture. Flooding does move soil and silt. In biblical times, the delta on the Nile was an area that was very fertile, a very productive area. And that's a very positive aspect.
Without the great forces evidenced in creation, there would be no cleansing, nourishing winds and rain. The tides and floodwaters of the world wouldn't have their opportunities to contribute to an ongoing process of land fertilization and renewal. The mysterious, awe-inspiring wisdom of God's creation is all around us. As far as we've been able to discover, the Earth is a unique orb of life floating in the vastness of space. Even a cursory glance around us for but a moment each day, might eventually lead us to echo the words written by the author of Psalm 19. The heavens declare the glory of God. The skies proclaim the work of His hands. Day after day, they pour forth speech. There is no speech of language where their voice is not heard. Their voice goes out into all the earth, their words to the ends of the world.